Session here we're talking about is operational center needs, and there will be some blurring between operational center needs and the session yesterday where we talked about activities from some of the other operational centers, and also ideas about how to make the Outlook serve operational needs and modelers' needs best. So we'll start out with Michael Sigmund, and he's visiting us here from the Canadian Climate Center and analysis. Oh, for modeling analysis. I was pretty close. Okay, great. Michael. What's that?
You've been there for a while. You should know. Eight minutes?
Yes, 8 minutes.
Okay, here we go. So I won't talk about center needs, but just I'm going to show some results of what we're doing in Canada, or specifically at the Canadian Centre for Climate Modeling and Analysis. So much of our, or almost all of our research is based on CANSIP's Canadian Seasonal to Interannual Prediction System, which is Environment Canada's operational seasonal forecast system based on two coupled models with interactive CIs. The initial conditions obviously are close to observations, and they were obtained by the so-called adaptation simulations. So in which we nudge the sea ice concentration, the atmosphere, and the ocean to observational products. However, we were not able to do something sensible with sea ice thickness. Specifically in these adaptation simulations, we nudged to a climatology. So the sea ice thickness initial conditions for 1979 were the same as in 2009, which is obviously not very realistic. We typically use a run for 12 months, initialized every month, and this is our Nowcast period. So this is a plot that British Edge showed yesterday. This is our skill that we get for forecasting the total anomalies as a function of predicted month and lead time. And the dots are statistical significant, so you see a lot of dots. This is a plot that Ed didn't show. This is exactly the same metric, but now verified against head ISST data. And you see some differences, and the differences are appearing at the longer lead times. And the differences can be explained by the trends. A large part of the skill is due to the trend at these longer time scales, and the trend in the head ISST, especially in March, April, is significantly smaller than in head ISST. So the take-home message here is that skill is not absolute, but it depends on the verifying observational data set, which can be quite different. So this is also a plot that Ed showed yesterday. This is the skill that we get after detrending. So this is how well our model predicts deviations from the trend. Focusing on September, we see that if we initialize on June 1st, so this is a time lag of 3 months, and later we get significant skill, but if you go back to May 1st initialization, then we don't have any skill. Hopefully, if we initialize the CS thickness, we can get additional skill at these kinds of lead times. Sorry. So what Ed also highlighted was the high skill that we get for winter forecasts. So deviation from the trend can be forecasted skillfully almost up to a year in advance. And to understand that, you can compare the skill that we get to observe lag correlations or persistence. And you see some kind of correspondence between the two plots. The point that I like to make is that as a dynamical model, it's nice to have skill from persistence, but you really have to beat the skill of persistence to get meaningful or valuable forecasts, because, well, you don't need a you don't need a dynamical model to get the skill of persistence. And fortunately, we get on average a higher skill than that of persistence, so that's a good thing. So this is from a paper from Bill Merrifield, which shows the fraction of forecasts for which the skill beats the skill of persistence. So indicated by red. So red is good, black is bad. And he did it for CANSIPS and for CFS version 2, for a bunch of different metrics, for total anomalies and detrended anomalies. And the main result was not so much a detailed comparison between the two, but the fact that if you create a multi-model ensemble, and these two models contribute to the NMME, you get typically a higher fraction of the forecast with a skill that beats persistence. So the red portion in the last column is larger than that of the individual models, typically. So there's some advantages of combining, creating a multi-model system, which was obviously known for variables like precipitation, but here we show that it's the case also for sea ice. My last slide is on CANSIS, it's a Canadian Sea Ice and Snow Evolution Network, which is almost an equivalent of CIPN. It's a 5-year partnership between universities and government. Its aim is to advance prediction of Arctic sea ice and snow, focus on Canada, to improve models and observations and process studies. It's arguably a little bit broader than CIPN because there's a large snow forecasting component in it, and there's also, we do things like detection and attribution. So we're on the web and on Twitter. That's it, thanks.
Want to take a question? We need to give you a microphone, no?
The CANSIP and NCAR models had very different variability depending upon the start date. So if you picked a particular start date, would that the advantages of taking the multi-model system have still been there, you think? Like if you picked CANSIP's best start date, would NCAR have added value and vice versa?
I think if you look at these kinds of plots, there is quite some correspondence between CANSIPS and CFS version 2.
But I think they don't see the early spring enhanced predictability, if I recall correctly. So.
Well, I think they do. Maybe there's somebody in the room who can answer that question better than I. I don't know where he is.
It's just like comment when you showed the previous slides, verification issue when you compare with the NISDC data and with the Hadley Center data. So I think that's actually a very important point because when we evaluate models, a lot of people use NISDC data, but the spatial resolution actually does impact your CIS extent calculation. And that's why we always use Hadley because it's kind of more consistent in terms of the spatial resolution and the model grid resolution. So I really think this is the point when we consider, verification issues.
Okay. we use HiDISSD for this.
I think we better move on, but thank you. That's neat. Trudy Wollebeen is next, and she works for the Canadian Ice Service.
Is this a pointer?
Probably. There's some people who have PDFs, that's why I ask.
Okay, so I'm just going to present an example of the seasonal outlook that's issued by the Canadian Ice Service jointly with the National Ice Centre under the name of the North American Ice Service. It's issued at the beginning of June each year, and it's a 90-day forecast, and it's for stakeholders like the Canadian Coast Guard, American Coast Guard, resupply ships, mining ships going into the Arctic, cruise ships, naval exercises, so all of those people that we work with directly. So for people who are not aware of what we call the NAV areas, the navigational areas, or the meteorological areas designated by the WMO, or these pie shapes in the Arctic. So Canada is responsible for 2 of these large pieces of the pie of the Arctic for ice and weather warnings and shipping safety. We don't yet have a mandate to issue seasonal outlooks for the entire area. We still just focus on the Canadian Arctic and along the Alaskan coast. It says here issued June 4th, that was last year. We try to go for June 1st, but everything in Canada has to be also translated into French, so depending how quick you are with that, sometimes slows you down. And a lot of the shipping industry doesn't like that June 1st date. They like to have something earlier, so they ask us to give them a pre-seasonal outlook, usually sometime in May, earlier if we can, but that's usually not possible. So the 3 main regions that we forecast for in the Canadian Arctic are the Eastern Arctic, Western Arctic, and Hudson Bay. The specific types of things that we forecast are divided into what we call events, which are dates of fracture, dates of open drift or less. So that's 4 to 6 tenths of ice concentration or less, and less than 1/10 of ice, although there may be icebergs present. And the other type of thing that we forecast is concentration. General concentration, seasonal average concentration. And we usually present this data in the form of a table, and then there's also a text description at the end of each table. And this is all done by one person. It takes about 2 to 3 months of work to prepare one of these outlooks. So just as an example, one of the tables, or a partial table for the Eastern Arctic, all the things that we are requested to forecast. So for example, Baffin Bay, the shipping route across northern Baffin Bay, when will the ice be 4 to 6 tenths or less concentration across that shipping route? So we give them the earliest date in our database, which goes back to 1968, that it's ever occurred, the latest date, the median date, and then what we think it will be. So last year, the median date is the 13th of July, and the outlook date was the 26th to 28th of June, so earlier than normal. And in addition to the tables of dates, each area is given a summary, so summary of what the ice conditions are at the beginning of the melt season, and then you have your outlook for June, outlook for July, outlook for August, and your outlook for September in terms of how the ice concentrations will evolve. So there's a lot of regions, and it's a lot of work. And this is just a very, very general outline of how the outlook is produced. The forecaster will start with looking at the accumulated freezing degree days over the past winter, how the freeze-up evolved in various areas, how the ice thicknesses evolved. If there was a lot of snow cover, did they keep up with the freezing degree days? Are they less than expected? So combining that with actual ice thicknesses and current ice conditions at the beginning of the summer, and then looking at summer air temperature outlooks where available. It's a little more complicated than this. The forecaster will probably also look at teleconnection indices and how they're evolving, based on their experience, the impacts that they have in different parts of the Canadian Arctic are taken into consideration. And then the last step, this is fairly new, so using guidance from statistical models. Prior to this, we always used analog years in our database. So you try to find a year which had a similar freeze-up, similar ice thickness at the beginning of the melt season, and a similar temperature outlook for the summer, and you go back in your database, try to find a year that had similar characteristics to your present year, and then use that year as your analog for the upcoming summer. But the problem was, starting around 2007, there were no analogs for for the years in our database. So we started relying more and more on statistical models. We have a MLR system model. We have an optimal filter-based model, which is like an autoregressive type model. The MLR is used for forecasting all the things in the table that I showed you on the previous page, so dates of events, route clearing. The OFB, or the optimal filter-based model, is used more for time series forecasting, so for Baffin Bay, which is this area, the evolution of the ice concentration in weekly bins through the melt season. And we also have a canonical correlation analysis model that we're testing for Beaufort Sea and for Hudson Bay. But all three models tend to have skill in the same places and no skill in the same places. So Baffin Bay does very well, the three models. Beaufort Sea, all three models just tank. They just have no skill. So it's not much help for the forecaster. So this is the last slide, just issues critical to the Canadian Ice Service, some things Adrian and I put together. Of course, we have a strong regional interest, the Northwest Passage being the key one. Fast ice and dates of fracture, dates of clearing of the ice, dates of freeze-up. How do we communicate uncertainty? I really like the idea of being able to say there's like a 60% chance of route clearing by a certain date. How can CIS make the most effective use of all the various model outputs available? So coming to meetings like this, you see there's a wide range of work being done. How can we incorporate that? And the one that I most directly want to use right away is Andrew's his 50-day forecast. If we could try that this summer, that would be great. And then, of course, what is the impact of initial conditions? So the departure from normal multi-year ice pack concentrations in the Beaufort Sea seem to have a big impact on how the melt season progresses in that area and things like that.
Thanks. I think we'll take the third talk and then we'll have questions, okay, to have a little pause between talks. The next speaker is, I hope I pronounce your name reasonably correctly, Wan Ku. Okay, Wan Ku. Wan Chu, beautiful. And he is from NCEP, and almost. I'll hand it to you.
Thanks. Yeah, yesterday a couple of talks mentioned the CFS performance, which is roughly comparable to other forecast systems. Today, I just want to look at the existing issues in this system, the problems, and I will focus on three of them. The first one is the inconsistency in initial CS concentration, and the second one is initial CS thickness possible errors, and the third one is the impact of model bias. Okay, initial concentration. The CFS version 2 is initialized from CFSR, Climate Forecast System Reanalysis. It's a coupled reanalysis system. The CS concentration, two analysis data sets were assimilated to CFSR. Before 1997, NASA team analysis was used. After that, INSEP, its own analysis was used. So here we are looking at August CS extent from CFSR, which is red, and black, which is a NASA team analysis. Clearly, before 1997, CFSR is slightly lower than the NSIDC archive, and after that, it's larger. So this means the long-term trend is weaker in the initial condition for CFS version 2 analysis. So corresponding to this, here is a forecast for September CS extent, which is red is 0 month lead, and blue is 2 month lead, and black is observation estimate. And we see the similar thing. So before and after, there's a jump between before and after 1997. So what this means is we need a consistent CS concentration analysis to represent the long-term trend. Actually, this weaker long-term trend we can also see it in the Canadian forecast system and the GMA models. Next, I want to talk about the CS thickness. Oh, sorry, I need to do something here. Sorry. Maybe this is good enough. Okay, this is better, not the best. Anyway, the September forecast for 2012 CS extent, and the black line is observation, and the x-axis is the initial month. So our forecast is for target is September 2012. So like this one is forecast from January 2012 for September, and the last one is forecast from August. So before June, the forecast is big. The error is very big, and after that, the forecast becomes better as the lead time reduced. So if we start from August initial condition, the forecast is quite good. So the question is, can we further improve this if we have better CS thickness? The answer is possibly yes. Here we compare the CFSR initial CS thickness anomaly for June, July, and August, and top one is a Pyramus anomaly for June, July, August. Clearly, the sign is roughly dominated by negative shading, which is blue, and in both analysis. But Pyramus anomaly is clearly is bigger. So we are just guessing if we make this the same forecast, but initialized with Pyramus CS thickness, the forecast could be better. And the third problem is the model bias. So I want to start from the right panel, which is December forecast for December concentration. And there's a blue lines there, which you may or may not see, like that here. Blue line is observed, 15% concentration. And the color is a model's concentration. It starts from 15%. So if you say color, that means that model concentration is 15%. And if it's white, that means it's lower than 15%. So we can see the model was not able to capture the formation of sea ice around the Bering Strait. So that's a big problem, because we have received requests to give a forecast for that particular region. So if we don't improve the model, the forecast will not be really of any use. So that is the CS bias. So now we trace back what could be the cause for that. And when we look at the SST, there's a big warm SST there, which is about 2 degrees or 1 or 2 degrees, which is pretty big. Yeah, 1 or 2 degrees. Now we further look at the surface fluxes. we'll notice that the model generated excessive solar radiation compared to observed estimate, which then is related to the cloudiness. So this means that the CS prediction is not just a CS initial condition or CS model itself, but it's very largely affected by atmospheric physics. So what we want to do is we want to improve this together with a few other things, but the development of forecast system is not continual. It's like a at NSAP it's like 7-year cycle, roughly. So next development implementation could be 2018 or after. So what we want to do is to do something between now and then. So we want to initialize CS forecast, CS initial condition from alternative data set like a biomass, and use another interim couple model, which has a better representation of the surface fluxes, and hopefully this will result in a incremental forecast scale. Thanks.
Thank you. Unfortunately, we're going to pass on questions because we are running late. I think we started a few minutes late, which is a shame, but that's life. And the fourth speaker is Neil Barton, and he's from NRL, Monterey. Doing two things at once is always a danger. All right.
All right, well, thank you. I'm Neil Barton, as mentioned. I'm at NRL Monterey, and what I'm going to talk about today is some of our development, what we're doing for Arctic sea ice prediction, and next is Pam Posey, and she'll be talking about some of the more mature things that NRL has been doing for Arctic prediction. So with that, we're largely on the development side for sea ice prediction. Oh, so the project, we're with the Earth System Prediction Capability, which hopefully Phil explains a little bit better later on. So NRL is interested in this idea of seamless prediction. So seamless prediction, if you haven't heard this, is this idea to use your operational models for short-term forecasting, for long-term forecasting. So it has the same sort of model framework for these different forecast lead times. And here's a graph that represents forecast lead time and basically diagnostic scales that we're interested in and sort of forecasts that we may be diagnosing. So day lead time, we get your typical operational meteorology, temperature, precipitation, so on. For a week, we get more of their polar lows, and then moving on and on, we get ice melt transition, sea ice extent, and then potentially Arctic oscillations. NRL Monterey right now is doing weekly forecasts. In an operational sense, they're doing 16-day forecasts for ensembles to get more probability. And eventually, we're currently diagnosing the models up to a month forecast time. And when I say NRL, I mean NRL Monterey with some collaborations with NRL's tennis. So what we have right here, or the long-term vision, is a coupled model. So once we get up to past 7 days, we have to be more interested in the coupling of the models for the fluxes that matter at those longer time periods. So well, the long-term vision is a land model, atmosphere model, sea ice model, ocean model, and a wave model with some sort of mediator or coupler in between. All the fluxes don't necessarily need to go through the coupler. For example, with the ocean model and the wave model, most the variables that are going across through the coupler are 2D variables, but with the ocean model and the wave model, they're actually 3D variables. So it's much more efficient to have them not run through the coupler. Okay. So the models we are using and which we're proposing to use for this system, and these are the global models that are located right here. I need to also mention that we're developing this at a regional scale also. So the same sort of setup with the type of models we're using at a regional scale. So currently, what we're using is we have atmosphere at 37 kilometers. Our ocean and sea ice model are pretty high resolution for global models, so at 9 kilometers, which we're getting a lot of the eddies within the ocean model globally. The mediator, I should mention, is part of the Earth System Modeling Framework with the National Unified Operational Prediction System. So what's currently set up right here is coupling between the atmosphere, the ocean, and the sea ice. So that's what we currently have set up and what we're currently testing at the time. So we've been running this coupled system and sort of more diagnostics and model development for about, really just about 2 months now. So HICOM and NavGem are fully data assimilated systems. In the sea ice model, we're using sea ice concentrations to assimilate, but we probably need to do something more with sea ice thicknesses. Just an example of the one of the forecasts that we're using. This is just examples. So we have the atmosphere model just forcing the sea ice model. Then we can look at fluxes total coupled between the atmosphere and the ocean. And this is run with just a data ocean. So the SSTs and salinities were all prescribed. And we can see we're getting to the point where we can diagnose the differences and what fluxes and what coupling matters in our system for, say, 10-day forecast. I ran this out for about a month and a half with a data ocean. I wouldn't take too much. So what this is sea ice percentages, and then these two different lines are two different observational data sets for sea ice concentrations. Yeah, it looks good, but I wouldn't take too much into this because this is forced with a data ocean. So we have SSTs and salinities. So if it looked bad, something really, really wrong is with the model and the coupling. Yeah. Okay. Since this session was called Observational Center Needs, I thought I should put a slide about observational center needs. So first, I broke it down into developer needs, which I think we all here know more about developer needs. This is just a list. I put sea ice thickness data twice because, for one, I think we just need a better handle on it. Yeah. And for data assimilation and using our models and initializing it. So it's very important. And then with the rest, we could all make our list. We had some really great ideas here, ice ponds, snow on top of ice. Some other things, some operational needs. A lot of these have been mentioned too. Sea ice freeze updates, sea ice melt dates, ice freeze season, and then what we're doing here, sea ice extents. A couple things I wanted to mention. Wave heights and waves were also mentioned as an operational need briefly in the discussions. But with talking to the National Weather Service, they're really concerned, or they get requests for a sea spray forecast. So they have problems with ships that you get a strong flow off the ice onto the water, and their ships out there, ice is up on the ships, and it can make very dangerous situations. So there's just, a lot of this has already been mentioned, and I want to just mention here again. So thank you.
Sorry. I can misread the schedule. No, not at all. I'm dying to hear your talk. Pam Posey is next from NRL and Stennis Space Laboratory. Let me put it on projection.
Okay, thanks. Now remember, Mississippi minutes are slower than anybody else's minutes, so let's be careful with that timekeeping thing. You know? Okay, I'll be quick. As Neil said, I'm with NRL down at the Stennis office, and we run our operational models located in the same complex that we're at the, and they run at the Naval Oceanographic Office, which is co-located with us. We do operational ice forecasting for the Navy. The system that we use currently is called the Arctic Cap Nowcast Forecast System. I call it the Arctic Cap model for short. Three components. We are fully coupled between the ice and ocean. We use the sea ice model, the HICOM model for our ocean, and then for the data assimilation aspect, we use the Navy's 3D VAR simulation scheme. Arctic Cap was declared operational last year, and every day the model runs and produces a nowcast out to a 7-day forecast of ice conditions such as ice thickness, ice concentration, and ice drifts. Ocean features such as such as temperature, salinity, and ocean currents. And let me stop right here and say, for us, thinking outside of the box is doing a seasonal forecast. You know, for us, we do these very, very short time periods. So when we produced a seasonal forecast and we were in the middle of the modeling as people that submitted to Sea Ice Outlook for the past couple of years, we were excited. Yay, we weren't outliers. We did fairly well. So again, that was thinking way outside of our normal box of interest. Every day the model runs, our products are pushed to the National Ice Center and also to INCEP at NOAA. All of our testing that we do, whether it be data assimilation or new physics in the model, gets done using the Arctic Cap system, but final implementation is in our global system, which is called GOFS, the Global Ocean Forecast System. Arctic Cap resolution and the GOF resolution at the pole is about 3.5 kilometers, 4 kilometers around the Canadian archipelago. So for the Navy, the ice edge location is extremely important. Ships can't get within a certain range from the ice. Again, it's important for submarines when they need to come up and for daily communications or if there's an emergency and they have to surface quickly. But the Navy has been used in passive microwave SSMI, SSMIS ice concentration since the early 90s. We have used this data because we depend on data that is in real time. We can't use historical data for assimilations in our operational models. This led us to a problem because we're tied to a passive microwave to update our ice edge location. We know passive microwaves have problems in the summers in detecting ice edge, detecting ice along the in the open water. They think that melt ponds are ice, so they call that open water instead of being an ice cover. So we tend to underpredict the ice edge in the summer months, and that is due to the fact that we're tied to passive microwave. So in order for a model to go operational, it has to go through an op test. The NIC was our op test source that completed our validation, and they suggested that we use their product called MACI, the Multi-Sensor Analyzed Sea Ice Extent product. This is a hand-derived ice cover mask, so it's a binary file, a 1 or a 0. Our Arctic Cap model is not used to reading in a 1 or a 0. We're used to reading in a concentration value from 1 to 0. So we worked with Florence's group at the National Snow and Ice Data Center in developing a high-resolution blended AMSR2 plus MACI product for us. I'm not going to go through this whole slide, but my main point of this is one of our metrics that we use to determine how well our ice edge is doing. We actually run the model assimilating different data sets and compare the model ice edge location to the observed observation. So on this chart, the first column here is what the operational model is now using. We take the operational Arctic Cap model, we assimilate the 25-kilometer SSMIS ice concentration daily into the model. We've looked at 6 different regions, and these are the ice edge errors derived from using the SSMI data. So if you walk over to column 2, that's running ArcticCap initializing using the AMSR2 data. So we get lower errors, which is not surprising because we're going from a 25-kilometer initialization field to a 10-kilometer initialization field. The last column, which we're very proud of, is the blended product that Florence's group came up with. Again, this is blended Macy product plus AMSR2. This is passive microwave AMSR2, but it uses this ice cover mask, and you can tell in most every region that we looked at, we have reduced our ice edge location by 40%. So, and we've been talking about how important data is at this workshop, and this just goes to show the operational models actually need high-resolution data in real time so that we can use it to make accurate forecasts. I talked just a little bit about our global model. We did the exact same test looking at the ice edge location, comparing the regional model, the ArcticCap model versus the global model. The global model has been updated using a more realistic initial condition. It assimilates slightly different, plus it has an improved ocean in it. And you can see in most of the areas, the global model has lower ice edge errors than the ArcticCap model does. The global model will be implemented by next year for the Navy. So just our connection to the community. We are extremely interested, and I think that we all are interested in ice thickness. I may say it twice because it is important, ice thickness. We're also interested in ice surface temperatures, too. We were lucky enough to be selected to participate in the NASA ICESat-2 early adopter program, and we're actually hosting a sea ice workshop in early August down at Stennis. Y'all don't faint. It's not that hot. Come on down. We've actually provided some ArcticCap products over here. This was an ice thickness field that Sinead Farrell requested so that they could start planning this year's icebridge flight track lines. So we try to be helpful to the community in what we're doing, because we feel like the more we reach out to the community, the more feedback that we'll get about our model and the more improvements that we'll be able to put into our model. Again, ONR is very interested in the Beaufort-Chukchi area right now. Scott Harper shared with us about their field work that's going, and we actually zoomed the ArcticCap products to that area so that they could have a quick look every day if they needed to. So we can easily supply these fields to people as they go out and they do field experiments or anything else that comes available. We'll be happy to share fields with you. And again, when we saw that our ice extent fell in the middle of the modeling efforts in the Sea Ice Outlook for the past 2 years, we were very happy. So thinking way outside of our box, but we look forward to participating in this year's Outlook. Not only will we run the ArcticCap model, but we'll also run the global system too. Thank you.
Thank you very much, Pam. That was really very interesting all around, 5 talks, and I'm sorry we're not going to be able to take questions because we're actually running a little bit late and you have to keep to schedule. But we have another session now about data assimilation and 2 speakers. So Frank Cocker is first on the list, and then Francois Massonnet. So I'll just tell you when it's 15 minutes, or do you want? Yeah. Okay. Do you remember where your talk was?
Yeah. Do you have a pointer? Okay. I'd like to talk about advanced data assimilation and design of observable networks. So especially the part of the design of the observing network is the brain behind it is Thomas Kaminsky, not me. And we are working, of course, not alone here, the co-workers. So we are doing no high-resolution modeling. We have a regional Arctic model, half-degree resolution. It's a sea ice ocean model only 20 layers on the vertical, but that's a model that we use in the sea ice outlook. And what we have is we have the adjoint of that. So variational data assimilation, what does it mean? You would set up a cost function. It's a misfit between data and your model. So we can handle every observations where we can write down the model analog. And of course, we need uncertainties, so I stick all the time to uncertainties. Here it's written in a general form where we can also handle non-diagonal uncertainties, but we are doing not that at the moment. And then we have some regulator here, it's a prior term. It's all our a priori knowledge. For instance, how good is our initial state? There we have to get some uncertainties for. And we have to do it for every variable we have in the model. So the red line is some state over time of the model. These are observations, and we want to bring our model within the error boundaries. So what we're doing is we vary the forcing, the boundary conditions, the initial state, temperature, salinity, ice conditions, and we can also handle model parameters. What we are doing is to generate the adjoint. If you want to minimize the cost function, it's fine to know where downhill is. And we do that by automatic differentiation. So we generate the tangent linear and the adjoint. We applied the system for assimilation windows of some days up to 2 years. And I would say that's the limit of adjoint data assimilation. So 2 years, then the system gets too nonlinear. Your gradients get very high sometimes. Our newest applications where I want to talk a little about is it's short-term ice forecasts. There we call our system ICEDAS. And the output is not directly, there's another model nested between, but it's used for ship routing optimization. It's a German project and it's called IRO2. What we are using is snow thickness, remote sensing data, ice concentrations, ice thicknesses, SMOS. So they are only good for thicknesses lower than about 0.5 meter. And we are using SST data. For this, we have local uncertainties. For the SST, not. We have run the system operationally from January this year to end of March. And we are using the ECMWF forecast. And the system was really tested on board of the research vessel Lance 2 weeks ago. So this is the output, not of the coarse resolution, the high resolution output. It's transferred to the ship through an active system. The color gives you the ice thickness. And then the HSVA, is the Hamburg Chip Basin facility, is doing some route optimization. For instance, if you want to come from here to here, straight line is maybe not fast. They said this is a good line here, and they tested that. And on this straight line here, they got stuck on the ice. So the system works more or less. So, but seriously, we are on board of Lance. We had also an EM bird measurements, or not EM bird, electromagnetic ice thickness observations. So in the next weeks and months, we will really qualify how good we are and what we can do. So, quantitative network design, what is that? We have all the observations here in the Arctic, but we really do not know what is the benefit of some observation. So if you want to answer some questions, like for instance, want to know the ice extent in September. We are designing, or what we are doing is, in a schematic here, we have our model, we have an assimilation system, the 40VAR system, and around that we have the QND shell, we call that. We put into the system some network configurations, and what we get out is the uncertainty or the uncertainty reduction of some target quantities. There is jet lag a little bit, sorry. Of course, there's mathematics behind that. And the brain is, as I said, Thomas Kaminsky. here are some references given. The point is, if you are doing a little bit algebra, you can see that the target uncertainty depends on the gradients, which we have, and on the a priori uncertainties. So if we put to everything that we have uncertainties, we can give you the uncertainty of the target quantity and also the benefit of observation. So we try to mimic in a very demonstrational sense another icebridge campaigns. We have observations of the 5th of April 2007, one flight and the other flight. We call that HARU1 and HARU2 because HARU is our co-worker here, and he gives us these flights here. And we assume that we know the uncertainties on every grid point here in the model of the observations, which is snow and ice thickness. We do not care here for representation error. We know the error, we assume. By the way, we do not need the observations. We only need the uncertainties. So the data we generate by ourselves. Come on. It's really true. You do not need the observations, you need the uncertainties here. The target quantities. We call that Chukchi, but it's not Chukchi. It's north of Chukchi, this area here. So our target quantities are the integrated ice area, integrated ice volume, integrated snow volume. And now we want to know what is the benefit within that area here to these variables of the observations of the two flights for the 10th of April, end of June, and end of August. So the observation was on the 5th of April. I forgot to say what we have to describe somehow the uncertainties. And that is 20 centimeters for ice thickness and as well as for snow thickness. And that example here. So our control variables. Normally in the system we have millions of control variables. It's not that easy to understand what's going on then. So we reduce the control variables to a reasonable size. And we do that by dividing the Arctic into 9 areas. This is area 8, I will come back to that later. So we do a perturbation. If we're doing a perturbation in the inner Arctic, it's the same on every grid point in the inner Arctic. And for the vertical, for the temperature and salinity in the ocean, we assume some profile. So at the surface is 1, and the depth is only 1/10 or so. So, and we need to know uncertainties. Also for the model parameters, like for instance H0. Our model is old-fashioned, so we have this H0 here, H0 lead closing parameter. We have to give an educated guess, what is the uncertainty. Sometimes it's not educated at all. But here we know that some are using 3 meters for that parameters. Recommended by Hippler was 0.5 meter. We are using 0.5 meter, but the uncertainty we say is 0.5 meter. Yeah? And we do that for everything. For the 2 meter temperature, 1 degree is reasonable. What is the uncertainty of the reanalysis product? I think it's higher than 1 degree, but we use 1 degree. Now we can evaluate our flights. HARU1. This is the uncertainty reduction after 10 days. So we start our model as the 1st of April, observations of the 5th of April, 10 days after the start. We have a strong reduction in the volume, in the ice volume, and the snow volume. No, in the ice area, it's not observed. Oops. After 3 months, the reduction is much lower, of course. But the area is as high or even higher, reduction is higher or even higher, it's at the same level than the other ones, because then the model physics acts. Ice thickness and ice concentration are not independent in the model. Yeah? So we constrain not the area, but only the thicknesses. We constrain as well the ice area. After 5 months, this flight has no information. So the flight was going over our target area. What is going on for the other flight? No skill for 10 days, but larger skill than here after 3 months, and even some skill after 5 months. Yeah, but it's easy. It's upstream information. we have the buffer gyre. So the information is transported into our region of interest. And here's the buffer gyre in our model. So we have something like that. But now we can go even further. We can look at all the sensitivities, the gradients which we have. And then we can see we have a strong gradient regarding the salinity in region 8. So what's that? Why is that? Here's an example from another data assimilation experiment we made, where we assimilated ice drift. And we found that the control, we can look after that after you have done the assimilation on your control vector. And we see that the strongest impact had the salinity in 500-meter depth. So why? Okay, in the buffer gyre, see you have the buffer gyre. You have the strong barotropic mode. Yeah? If you change the salinity here, you influence the ice drift in the buffer gyre. And that we can see also in our network tool here. By assuming we would have had perfect salinity information, no uncertainty. This is HARIO2. After 3 months, more or less the same information. But here you can see slightly better uncertainty reduction if we would assume that we have perfect salinity observations. So that can you learn from such a system. What are the next steps? We evaluated the benefit of 2 flights. So we found that upstream information is most powerful for longer term predictions, but the reduction is small. That might be the reason why Jadilun is not seeing any more in September, if he is doing data assimilation. Information on the ocean state is important. Yeah, we need information of the ocean for a good prediction system. We are doing here only rough assessments. It allows us to qualitatively understand the system. Of course, more validation is needed. And we will render it step by step more realistic. So we will increase the set of control variables, do it more realistic. And we will skip the target quantity. We are aiming at using the Barnett Ice Severity Index, because that is used for in the oil and shipping industries. Thank you.
Thanks very much, Frank. And Francois, you're next. I should say I actually asked both of these speakers to speak on these topics because I wanted us to consider how we could use data assimilation to, do you have a new talk?
No, that's a pointer.
Okay. To use data assimilation to actually inform model observations. And so that's why they're getting a little bit longer to talk. So.
Yeah, thank you. Okay, so here's the problem. We know that we benefit from an increasingly large network of observations of the sea ice cover. And still, these observations are very variable, but they're only a small part of the full picture. So they are very valuable, but they're not sufficient to characterize properly the whole sea ice state, the whole ocean state. And the problem is that we know that a significant part of the memory of the system that will be used for advancing predictions is probably residing in this information on the full sea ice state. And to make the picture even more complicated, we know that the few observations that we have a very large uncertainty. Well, they have uncertainty. And so clearly at this stage we need another source of information to complete the picture. And this source of information comes from the models. The models have the advantage to explicitly simulate all these variables, but they are models, so only approximations of the reality. And how to optimally combine these 2 sources of information, so observations on the one hand, models on the other hand, has a name, and it's called data assimilation. And data assimilation is a really fascinating subject on which I've been working for now 2 years. It's fascinating because it has a very strong mathematical background and basis, as Frank showed, but also because it's really a tool that is making the connection between 2 communities, the communities of people that make observations and community of modelers. And I think it might be a very promising tool for advancing predictions in the Arctic. So I want to go in 2 steps and first look at a very simple sea ice model to really understand what are the central ideas of data assimilation, and then move to a more operational model, large-scale model, to see how data assimilation can help improve the prediction in the Arctic. When I'm saying I'm using a very simple model, it's a very simple model. This is just one flow model with no ice concentration. It has only 2 variables, ice thickness and surface temperature of the ice. So 2 variables. And basically it's responding to changes in fluxes from the atmosphere. Now we can suppose that we have observations of sea ice thickness, and we want to assimilate sea ice thickness in this 2 variable model. And this is the result. No. This is the result. So we have time here, we have sea ice thickness here. The blue curve is the reference model without any data assimilation. The red curve is the true thickness that we cannot even observe because the observations have uncertainties. And what data assimilation will do is just update thickness in a way that it's consistent, so that in the end you will have the green curve, which is what you call your reanalysis, and which is a kind of interpolation of the observation, and which is consistent with the true thickness. But that's not a big deal. This is just what we could call primary nudging. And the real question that we should ask ourselves is what happens with the other variable, which was surface temperature of the ice in our model. So I'm going to focus on this box here and look at what's happening in my ensemble. So I have here 100 realization of my model. I perturb the flux in the atmosphere for each of the member. But even if I apply some perturbation in the ensemble, I have some structure in the model. I have relationships between my 2 variables, sea ice thickness and surface temperature. And when you do simple nudging, if you have observation somewhere of sea ice thickness, when you do simple nudging, what you do is just you bring the gray dots closer to observations, but you forget one important thing. You don't update the temperature of the ice at the surface. And what you do if you do simple nudging is that you just break the relationship in your model between the 2 state variables. If you break these relationships, then it may have very undesirable consequences for predictability, because you might bring your system into an unbalanced state, and you may just lose predictability after the first step of initialization. So what's the way out? Well, if you want to go forward, you have to take into account that you have some structure in your model and update each of the member to keep every dot inside this envelope of model forecast. So this is very much the key of data assimilation, multivariate data assimilation, is to take into account the structure of your model when you assimilate one variable to update the other. So really, this is the first message that we cannot do data assimilation on one variable only. We have to consider the full CI state. Now, if we move to a more comprehensive CI model, the questions are essentially the same, which is a good news. The first question is, how do we make the interfacing between the grid cell information that is given in the observation and the subgrid scale information in the grid scale information from observation and the subgrid scale information from the model? How do we update the variables that are not observed? The second point is, how do we make sure that we pour the necessary information to give the memory, the necessary memory in the system, and to improve the prediction? And the third question is, how do we make sure that we keep the system at all times in good dynamical balance? And we are doing this with an ocean sea ice model, which is NEMO and LIM3, which is followed by atmospheric reanalysis. And the answer to this question is very simple. It's the same for the the simple sea ice model. You have to account for the fact that your your model has some internal structure. You could think that this is the observed ice concentration, and here it could be ice thickness in the first ice category. It could be the SST, it could be SSS, could be snow depth, whatever. As long as there is a relationship between the two, you have to account for the fact that you will update these non-observed variables. But the point is that the correlations are not obvious in large-scale models. Yesterday we had a nice image from Stefan about what he called an old paper of 2003. It's maybe old, but it's still valid and very interesting. And I have here shown similar results with our model. The maps are showing the correlation between concentration that we observe and thickness in our ensemble. So we have 25 members. Each of the members is perturbed by changing the atmospheric forcing. And in winter, it's pretty much what we all think here. With higher concentration, we have thicker ice, which is just a thermodynamic argument. But in summer, it can happen that we have these negative correlations. Because in summer, my interpretation is that we are at temperatures of the air that are above freezing point, and that the winds play a bigger role in shaping the ice cover. If we have anomalously large winds, then the ice will pile up easier and will increase ice concentration, increase open water, decrease concentration, but increase ice thickness. So it's not surprising that we have this anti-correlation in summer. But in any case, you see that the way that variables co-vary in your ensemble is not obvious at all. Now, is it relevant for prediction? Well, I think it is. This is a plot that we saw a version of that plot yesterday. It's showing the error in September forecast in the Arctic for ice concentration for several years. The red curve is the control run, so just forecasts without any initialization. And the blue curve is the error for initialized run. So when we assimilate concentration and let the model evolve for 6 months from March to September. And you can see that systematically we have an improvement. Just from the information of ice concentration, we have an improvement in the simulation of September, just because of this mechanism of ice concentration, ice thickness. So I think this is promising. So yeah, if we account for the fact that concentration and thickness are related, but that is not obvious, probably we can move forward and advance Arctic sea ice predictions. So I want you to take home 3 messages. Yeah, the first one is that you cannot do data assimilation just on one variable. That's the only thing that you will do is probably to bring your model out of balance, which is even worse than doing nothing, I think. The second point is that it's not easy to update not observed fields, and you have to make it in a very formal way. And the third point is that it's necessary and worthwhile to do such data assimilation, I think, if we want to improve the predictions using large-scale models. Thank you.
Thanks. We have time for 4 minutes of questions. So would anyone like to ask a question? And maybe we'll get a microphone runner in hand. And it can be either to Francois or Franck.
I wonder, when you compare the errors for initialized versus uninitialized, are the uninitialized run, don't they have any SST even information? I wonder, do they have any information about sea ice that's not concentration? And do you really think that the currently assimilating concentration will improve this data assimilation?
So this non-initialized run, I think you're right, is not really not initialized because it's forced by atmosphere, and the atmosphere itself is a reanalysis product, meaning that it's been run with prescribed ice concentration during the reanalysis stage. So we indirectly use twice the information of, we use the information of ice concentration here indirectly, and here we use it twice because we assimilate concentration and we run with a prescribed atmosphere, which is based on itself on the ice concentration products. So it's just to show this is just showing the pure sensitivity of the seasonal hindcast to initial conditions. The only difference between the two is the change in initial conditions in March.
Yeah, I was just going to ask, obviously you show the link between ice concentration and ice thickness in the model. Obviously you can either take the mean ice thickness where there is ice within a grid cell, or you can take the volume of ice per unit area in your grid cell. And so whether that would change the conclusions from the discussion you showed earlier.
So the correlation that I showed are between concentration and in situ thickness, so not including open water.
Yeah.
And your question is, would I have the same correlation if I would include concentration, open water?
If you go to the previous slide,
Yep.
So that was, yeah. Okay, so this was all from.
But it was a generic, just to say how to update variables that we do not observe compared to the one that we observe.
Yeah. Okay. Yeah.
We'll take one more, and I think.
A slightly more general question: is anyone thinking about assimilating sea ice age or something like that, where we have some observations? Cecilia's thinking about it, and it depends if your model's got ice age output, presumably.
It does. It does have ice age, although I think it's a tracer in the model. The problem I see directly is that definitions are not the same in observation and in models. In models it's a tracer. In observation it's, I guess, I'm not a big specialist on that, but I think you trace ice and you deduce for how many years or something like that it's been there. And so I think the definitions are different. And if you, maybe I said something wrong, but for the observations, but there's a risk that you will assimilate something that is not exactly the same in the models and in the observations. It's a bit like if you were to simulate thickness against weighted open water weighted thickness or something like that. So.
More categories.
Okay, thank you very much. That was very informative, and I will now explain that I messed up on the schedule. I obviously need to see my eye doctor, but I switched the two sessions. So we do have links with PPP and ESPC next. So Gunilla will start, and I think we'll have time for a slide or two from Vladimir Ryabinin later too, before the end of this session. That's our plan anyway.
Okay, so my name is Gunilla Svensson, and I'm from Stockholm University, from the Department of Meteorology and the Bolin Center for Climate Research, and I'm an atmospheric person, an atmospheric modeler of small-scale processes like turbulence and troublesome clouds. That's my interest, and surface fluxes as well. But what I'm here talking to you is that I was asked to give a presentation about the WWRP Polar Prediction Project. And I got some slides from Thomas Jung, who is the chair of this project that started last year. It was already 2012, started a bit. And it's planned to be a 10-year program. And it's a legacy project after the Thorpex. And while I don't have to motivate you for why we should care about the Arctic and Arctic prediction, this is something that this report that I guess you know about would talk about opportunities and risks, and we need to know something more about polar prediction. So that's all about. And that's summarized in this mission statement. So it's to promote cooperative international research enabling development of improved weather and environmental prediction services for the polar regions on timescales from hourly to seasonal. And there is another project that is under WCRP that takes on from the seasonal and onwards. And I think you'll hear a little bit more about that later on. And there are connections between those two projects as well. So who is doing this? There is a steering group that was formed, and I'm not the only one in this steering group than that's here in this room. So if you want to talk more about details about this, you can talk to Marika or Don, myself, or Johnny Day, who's also here. And the rest of the people you see here. We had a meeting here in October talking here in Boulder. The last steering group meeting we had. And there is a science plan and an implementation plan, and I'm just presenting parts of it here. So there are the research goals that are divided under 3 different umbrellas. So we're really focusing on what is asked of the community, what do we need, what type of applications, how can it be useful, and also verification, which is in the service-oriented research. And then there's a large focus on the forecasting systems to improve them, improve all sorts of different parts, which involves more observations or better usage of observations, modeling, data assimilation, and ensemble forecasting, and what we can learn from all this. And then underpinning research, which would be predictability and diagnostics and global linkages. And there are some flagship themes that are identified. So we have the CI's prediction, explore predictability, which is this group is of course a very good reference group for doing things together. I mean, we don't have any funding to really do any science there. What we do is coordinate and help facilitating. So we're really interested in having dialogues with groups like this and to plan research together with you. And there is a lot of initiatives, as you've heard, during these days to develop a couple of prediction systems, but how to do it and how to do it in a good way and what timescales you're looking at. There is a lot of discussion of the linkages between polar regions and lower latitudes. So if we improve things in the Arctic, will that help for the mid-latitudes? And that's very much focus on that. And then we think that we need to improve the availability of already existing observations, so to facilitate that, and then also add more information, more observations, and more modeling experiments to investigate more in the year of polar prediction. So, well, I don't need to explain to you that we need forecast for this. This ship was frozen in, and it needed, and then they got a wind turn. Finally, the wind has turned, and a crack in the ice has developed, which allows us to move slowly northwards. So and that, of course, you want to know when and where that will happen, and that's really a challenge to forecast that. So there are some experimental things doing really high resolutions in global models, and you get lots of details, but how to verify those details? Are there any good information in it or not? In what timescales? Since I'm an atmospheric scientist, I wanted to bring up one result that a colleague of mine have done in Stockholm University, where we looked at the atmospheric processes and if that can have an impact on the predictability. So this is a study that was published last year. And if we look and sample just the years that are outside of the mean trend, so outside of the lines there, so we have years with more sea ice loss, and you look in this region, see you have less than normal sea ice in that region in the end of the summer. And then if you look in the springtime, you look at the fluxes from the atmosphere. So in the top you have the long wave, the latent insensible heat flux in the red, and you don't see anything particularly there. But if you divide them into the components and you look at the long wave down, you see that you have a big anomaly here in the spring that then leads to, or it looks like this has an impact on the minimum that you're reaching in September. And I think that sitting here and thinking that might be the reason why we have different predictability depending on where you start, because this can then already have preset the conditions somewhat in the springtime that has an influence on the rest of the season. But that probably doesn't hold for all years, so those are the extreme years in there. So some research from Thomas Jung's group looking at these linkages with the lower latitudes. So this is the change in forecast scale at the 500 hectopascal region when relaxing the two analyses north of 70 degrees north, so just in the inner smaller circle. And for a day 1 to 5 forecast, you don't see much outside of that box. But for the longer term, so the 6 to 10 days and 11, 30 days, you see there is some spread of continents to Northern Europe, and also the continents that you have some more predictability by correcting the errors, by keeping the Arctic into a more true state. And he's also comparing that to doing a similar kind of nudging experiment in the tropics. So where you, when you're relaxing your results to the tropical results, and there mainly you see that the information is spreading over the ocean northward, and you get an improvement there. So those are very different, and this can be used then to motivate why we need to improve, and how should we improve? Well, probably we need to improve the observational system availability, because this is how the situation for, well, a particular day, just what's going in, and there is large areas where we don't have so much observations. So that's one of the motivators for the year of polar prediction, where there's lots of different things that are planned, like doing more observations and doing more model experiments. And something that we've talked about, which would be interesting, is to do more of transpose CMIP experiments to try to gather data so we can do more concentrated research. Some really high resolution modeling, what can that be? And if you're more interested, you can look in the implementation plan. But since there have been so much talking about, well, okay, so this is the year of polar prediction. So we are now in the pre-phase, and then it's planned to be between 2017 and 2019. And then there is a consolidating phase afterwards. So one thing that is that I think would be helping, and that's it's in this, is the plans for having a new Shiba type of experiment, the mosaic, where there is lots of people. And I got this slides from Matt Shoup, who is leading this effort. And there are lots of other names here, and some of the people there you find here in the audience as well. And there are then plans to do different types of research experiments there, and it's like a three-part approach to have a observatory and then a network of spatial measurements and the coordinating modeling that goes along with this, and that's coordinated with then the polar prediction project. But the main idea is to have a heavily instrumented manned ship-based Arctic Ocean observatory to drift with the ice to make comprehensive coordinated observations of the Arctic, and going through the atmosphere, down through the ice, and into the ocean. So you have co-located observations of everything that we think matters in one location for a time period. And that can be really useful for both evaluation and model development. And this is this plan for having this track then, so you would have this drift. It's in the phase of getting financing for this, because this is not this is an expensive expedition, and there are lots of work going into that. So some upcoming events for the polar prediction. There is meeting in Helsinki next week, and there will be a polar prediction session at the Open Science, the WLBOP Open Science conference in Montreal in the summer. We will have a next steering group meeting there. And then you've already heard about this linkages workshop in Barcelona in December. That's also part of the efforts. And if you have more information, you can talk to us who are here, know more, or you can go to the website where there's lots of information. Thank you. Okay.
Anyone?
No.
Think of one during the break. Okay, thank you very much. You can see there are many reasons why we have a lot in common, and it will be important to stay in touch. Do you see your talk in here? You said you uploaded it, right? Is it on the desktop? Oh, good job. Nothing else is in there, so you're good. That one. Okay.
Okay, so I'm going to talk. They asked me to talk a little bit about the Earth system prediction capability and a little bit about this interagency Arctic Research Planning Committee, and I'll say just briefly few words on the NMME project. So we're kind of in acronym land. So for those of you who don't know me, I do wear a number of hats. Fortunately, neither of these two, but I'm talking to you mostly today on behalf of the Earth System Prediction Capability, but my real day job is I'm project lead for this DOE climate, ocean, and sea ice modeling effort that develops the sea ice model. For example, Elizabeth works in our team, as well as the POP ocean model and the community ice sheet model. So, okay, so the Earth System Prediction Capability is a multi-agency effort. Little bit of history. It sort of began with the then oceanographer of the Navy, Admiral Titley, and others kind of looking at the fact that operational communities were looking at pushing their forecast to longer timescales. At the same time, the climate community was looking at things like decadal prediction, and they were looking more operational-like. So there was this timescale in between, and there was some interest in both communities at looking at some common problems there. So Admiral Titley made a sort of a grand tour of a number of different both operational and climate centers to try to generate some interest there. So in the end, there was sort of a committee put together to look at are there value in predictions between this operational typical day to week timescales and in between that and the climate kind of interannual to decadal to century timescales. So it's led, even though it's an interagency group, it's led mostly from the operational side, the NOAA and Navy. Dan Eleuterio is the program manager in ONR, and Jesse Carmen, the program manager in NOAA. Neither of them could make it because there was another ESP demo project that's having a meeting at the same time. So some of them are down there. But they did end up, as a result of meeting with a bunch of interagency representatives, to try to define a few kind of demonstration projects, and I'll say what I mean by a demonstration project in a little bit, but they chose 5 of them. There's a tropical cyclone project led by Melinda Peng at NRL Monterey. There's one on trying to forecast blocking events led by Stan Benjamin in NOAA. So I got tasked with leading the Arctic sea ice prediction, and that's an interesting story that I could tell you over beer sometime. There was one related to AMOC that Jim Richmond at NRL Stennis is leading, and one in coastal hypoxia, and that's the other meeting that's going on this week, led by Greg Jacobs at NRL Stennis. So as we sort of got into these, they ended up pushing more towards shorter timescales. So a lot of these projects are really looking at week to seasonal and not necessarily seasonal to interannual. I think the sea ice is maybe a little bit of an exception there, and AMOC. But in some sense, they didn't come with funding to the table as a specific program. Some of the agencies involved have freed up some of their funds towards some of these projects, but it's been kind of on an agency by agency basis. So some agencies have redirected some of their internal funding. There was a NOP call recently on computational performance for some, so we were able to, for example, get some funds for improving performance of the sea ice model through that, primarily because of this ESPC connection. Yep. Oh, so NOP is the National Ocean Partnership Program. It's been a long-term program. So again, because there isn't a lot of funding behind this, most of these projects have been kind of largely organizational. So we're trying to organize the communities around these problems, and that's particularly true for this one and for AMOC, where there's already a large community, US AMOC and CRP and other groups already focused on that. So you guys all know why Arctic prediction, but certainly NOAA and Navy have a strong interest in supporting both kind of operations, and they have the mission to supply forecasts in these regions anyway. So they had a strong reason for doing that, and you're certainly seeing increased activity in the Arctic. You saw this picture of the natural gas carrier Obe yesterday. So I like to joke that in the past, ships used to get frozen in, and you'd either freeze to death or eat your crewmates to survive. But so these guys eat their crewmates. It's a dietary choice. It's not. So, yeah, a little slow on the uptake there. So at the time this all started, there were lots of other things going on. So this NRC report came out. They had a workshop looking at seasonal to decadal predictions of Arctic sea ice. The Sea Ice Prediction Network proposal was under review. So right around this time, the ESPC held a workshop to try to define these demo projects, and Cece and Marika and Pam was invited but couldn't make it, but I think either Jim or Greg gave her talk. So we tried to kind of define the goals of what a demo project might look like. But if you look at the NRC report strategies, and I'll skip here, I mean, what we ended up coming up with was pretty much taking those NRC priorities and trying to define kind of a model around it. So again, trying to unify the community around some of these things, evaluating the existing seasonal prediction methods, looking at potential process-based studies or experiments, particularly focused on kind of this change to first-year ice, model sensitivity studies, and then continued model development. And that's sort of what shows up in Sea Ice Prediction Network and a lot of the work that many of us are doing. So in the end, so again, it's been largely an organizational effort so far, and you guys did the hard work and created the Sea Ice Prediction Network. So we basically have co-opted that. So since you guys matched the goals we wanted to address anyway, so like it or not, you guys many of you are working under the ESPC demo project. So this, yeah, exactly. So this project does form a core that we've actually been able to use, in combination with this ESPC backing. So when the Sea Ice Prediction Network was funded, it was primarily an NSF project, and you guys had goals of contacting the other agencies. And at least when we contacted our DOE sponsors, the fact that we had both kind of ESPC backing and the NSF-funded effort already there gave them an incentive to kind of add on. And I know ONR has added additional funding as well. So again, it performed useful purpose for kind of uniting the community that we could take to sponsors and be able to get additional resources. So now I'm going to switch a little bit to IARPC because some of you have heard a little bit about this. So this is the Interagency Arctic Research Policy Committee. It's largely a committee, I call them G-men. So Scott, you're a G-man. This is Scott right here, yeah. But mostly it's a committee of federal program managers trying to, they were tasked with coming up with the national Arctic strategy and implementation plans for carrying out that strategy. So it's an interagency effort again, but really driven by the agencies themselves and their representatives. Although they have solicited input from community leaders, so I know many people in this room have given talks to the IARPC, particularly the Sea Ice implementation sub-team as part of this. So many of you have given presentations over the phone to these con calls, but there is likely going to be kind of an expanded opportunity for others to provide input for that. And Scott can correct me if I'm wrong there, but I think that's the plan. Yep. So that's all I'm going to say about that. Again, this is just a kind of a national effort to try to get the agencies to work together on carrying out that strategy. And then finally, I'll talk a little bit about NMME. So this used to be the National Multi-Model Ensemble, but then the Canadians joined, so now they changed the name to North American Multi-Model Ensemble. And this is probably an incomplete list of the models that are participating, but the idea, again, was to take these mostly from the operational side again, although CESM is maybe an exception there, to try to push these predictions to seasonal interannual timescales. So NOAA has been kind of distributing the forecasts from some of those. So they distribute things like 1 month, 3 month anomaly forecasts, some Nino 3 data, and other products that arise from these. But it's a continuing forecast system. So it was somewhat aligned with ESPC in the sense that ESPC was also trying to push these longer timescales. So I mentioned earlier during one of the comment periods that they did ask us for input on what sort of output fields and diagnostics they should put out. And I think in the end they got so much input that they couldn't afford to output everything that everybody wanted. So they had to make some decisions there. But that's kind of a brief summary of what NMME is doing. And certainly you could probably mine some of these forecasts for some of the information you want to see in this project.
Why isn't it international?
So that's a good question. I don't happen to know. But yeah, I think partly it's just a logistical thing. It's easier for agencies here to combine.
Sorry.
Thanks. I think I realized that it's pretty difficult to speak after Phil, and that this will be more or less a G-man talk. So, but being pretty serious, I would like to state that actually now, when we look at what people think, there is now a feeling that we are living in an era which looks to me like pre-Toga era when it comes to El Nino research. I think we have huge promise for Arctic prediction and prediction of polar regions in, for example, for the seasonal scale. So what I'm trying to do here is I try to, you're a scientist, I'm a G-man, so I'm trying to help coordination of certain activities. And so I think I would like to try to map what's happening, at least in this audience, on what I would say coordination bodies would think. So there is some disciplinary research that you are doing. This research has to be uptaken in some prediction activities, for example, experimental prediction activities. There are some external requirements for success of this research, and there are some arrangements that need to be followed or established to make it successful. And of course, there are some opportunities. I would like to just have a few slides about this. So disciplinary research, I think we speak about here mostly about CIs, of course. Similar activities, trying to identify sources of predictability exist in other domains. In atmosphere, in land surface, people are pretty enthusiastic about soil moisture and snow. In stratosphere, and of course in the ocean. We didn't speak enough about ocean and the influence of North Atlantic on what's happening in the Arctic Ocean and even hydrology. And actually, Wislav spoke about this. So when it comes to this disciplinary research, your focus is mostly on model improvement, improvement in fluxes, how different components associated with ice interact, and data assimilation development. And of course, when a lot is sometimes is happening only in interactive mode. For example, some stratospheric models, only with high top, with well-resolved stratosphere, are able to produce some processes that are important for the ocean. So I think we need to bear this in mind. And we need to focus more on the processes, on teleconnections, and also on large atmospheric variability modes to understand better what dynamics, what is behind the modes of atmospheric variability. I think WSRP is going to embark on this pretty strongly. Then we need to uptake this research and this in prediction. This happens mostly in modeling groups, various groups. So WSRP is trying to help these activities by proposing certain interdisciplinary experiments. Drew also already spoke about this climate, excuse me, it's the wrong acronym, Climate System Historical Forecast Project. And it has a subcomponent, CI's Historical Forecast Project. Also, I think the working group on coupled modeling will be very much interested in hearing from you on what's important in terms of coupling from the viewpoint of CIs. Ocean Model Developing Group. Also the working group on numerical experimentation that tries to understand how to move forward models for numerical weather prediction and climate models. And we do this in partnership, for example, with IASC for the Arctic. So there are some external requirements. I think what hasn't been discussed here, and this is really, really a very serious thing, is the observations in the Arctic Ocean are made mostly in research mode. They are not exchanged. There is almost no deep sea observation exchange in real time. So, and why it's happening? Because there is no push for this. Because those who make decisions about this, and also who allocate funding for this, they don't see the link between benefits of societal benefits of Arctic prediction and the funding that is required for the Arctic Ocean observing system. So we are trying to propose some links that will show to decision makers that without Arctic observations, sustained Arctic observations, it's impossible to get the societal benefit. Technical considerations. Now, I think what's happening in the world is the real revolution in data accessibility. For example, the CMIP archive is fully available through this Earth System Grid Federation. In the climate experiments, we advocate mostly for NetCDF format. But of course, for real time, still the world is working with grips and grids, mostly with grips. So we're now trying to establish databases, and CMIP is available, as I said. HFP, the seasonal prediction experiment, is also the data is available. There is now an idea to promote opposite database. So what I would like also to call on your attention is that there is huge experience indeed in verification of meteorological forecast. They not only are able to come up with quantitative measures of the skill, but also there are some groups that evaluate the societal input. So, and also the new approaches for evaluating models that are used in long-term prediction, because you cannot verify long-term predictions, but there are some considerations how to discern different models and their qualities. So now I'd like to present you, this is almost my last slide, merger opportunities. Gunilla spoke about the polar prediction project and the year of polar prediction. So what is really important there is I think it's a unique opportunity, really. This will be almost a 2-year experiment, which will have a very strong in situ component, very strong satellite snapshot. And the idea is to generate an assessment of energy balance of all components that are important for prediction. You can really, really make progress in modeling in this. And it will be done at different spatial timescales, which is also important, upscaling. So this is really, I think, a unique opportunity. And then this will result in massive multi-scale prediction experiment. So the design of this new phase of coupled models and comparison experiment is now ongoing, and CI's community is invited to contribute to it. Also, there is a project that is focusing on seasonal to sub-seasonal scales between the World Weather Research Program and World Climate Research Program. And Tomorrow and the day after, we're going to have a meeting on Polar Climate Predictability Initiative. And also, under the Climate and Cryosphere project, there is now an attempt to establish a sea ice forum, and Alexander Yan, who is now here, is running this. So there are many communities that can help you to achieve success in what you do. And this is basically what I wanted to tell you. So there are many opportunities to move forward in your field. And this is the slide I would like to also to show to you, because tomorrow we are going to have a very important event, Sentinel-1A launch. If you have jet lag, then you can watch that. Thank you.
Thanks very much, Vladimir. Any questions for any of the last three?
So I have a question about organization of science by these big programs, because it seems like there's just so many activities that are trying to take on polar prediction. And at some level, there's not that many of us that do polar prediction, right? I mean, so how are we going to coordinate things? And are we, or how did this work for other sort of projects that are at this stage? But it seems like every workshop I go to, I hear about TUNO initiatives related to polar prediction, and I can't keep up.
I understand. But I would like to draw attention to the CMIP6 and old CMIPs. What's happening is that many groups agree on common protocols, on common data for experiments, then they run their models. And I already presented to you the results of this climate chemistry model validation experiment. When the first phase was just, absolutely, there was no convergence. Now we have convergence, and these results were used in prediction of the stratospheric ozone layer for the 21st century. So such things, like common protocols, helping people to speak and identifying common data sets, this is how it works. So this is my view on this. So not really trying to kind of impose discipline and affect funding. We are providing opportunities for cooperation. That's how it should work. And I think something like this will be beneficial. And this Polar Climate Predictability Initiative is just an attempt to highlight what is possible to do by collecting common knowledge, bringing together the communities, and then trying to propose something which has perspectives. I don't know if you responded.
Yeah, maybe I'll just follow up. I totally agree with everything you're saying. I'm just saying that I think there's like 5 or 6 groups that are trying to do that, and I wonder if that's the most efficient way to do things. And yeah, maybe I'm just spouting off, but I think it's an important issue, because I don't want to go to 6 polar prediction meetings organized by 6 different groups every year. I mean, that's a lot of...
At least we had them back to back. So PCPI in SIPN.
Right, and Jen, I think that's the why I was kind of joking that we co-opted the Sea Ice Prediction Network. I just didn't want to add yet another project on top of everything. You guys had already kind of self-organized, and we just wanted to take advantage of that.
And I also think it's important to see that PCPI is a more international project, while SIPN, at least all of the funded participants on the team are in the country. So PCPI actually didn't exist when we started, so they didn't yet claim us. I'm in both, so which us am I? I mean, PCPI hasn't yet claimed SIPN, but we'll be talking about that.
I think the idea is not to take, the idea is to give. So tell us.
Thank you very much for that point. All right, well, with that, we'll take our break, and we'll come back at I'm going to read the schedule. At the right day. 3:15 is the coffee break, 3:45. And the last session will be just 45 minutes when we'll adjourn at 4:30. Okay, thank you.